Flipped classroom video for Maths A2 Unit 3, Implicit Functions. So what are implicit functions? Well, a good way to look at it is to start with what we already know about, which is explicit functions, and you're used to them, and these are where one variable is defined completely in terms of another. So for example, we have y equals x squared plus 3x plus 2, so y is defined in terms of x. Or, for example, we could have z equals sine of 4t minus 3. So z is defined in terms of t. And if we generalize this, the first one is an example of a y equals f of x function, and the second one is an example of a z equals g of t. So that's a function of t. Z is a function of t. And in these examples, y or z, they are both dependent variables, and x is the independent variable in y equals f of x, and t is the independent one in z equals g of t. So, implicit functions are functions where one variable is not completely defined in terms of another. So the function is in a sense implied. For example, we have x squared plus y squared equals 4, and you might recognise that as the equation of a circle. I hope you recognise that as the equation of a circle, in fact. Now, if we try to make this equation explicit, then we can rearrange it to get y equals plus or minus the square root of 4 minus x squared. But we've got a problem, because is it plus or is it minus? We can't have a function where we've got two different answers for various values of x. So this is a good example, or a simple example, of why implicit equations are useful, because we want to be able to define a circle, and x squared plus y squared equals 4, for example, does that, whereas if we were going to use the explicit, we'd have to have sort of two parts. We'd have to say y is the square root of 4 minus x squared, and y is minus the square root of 4 minus x squared, which is messy at best. We'll have a look at some examples of implicit functions now, and within astronomy the conic sections are very important, and the circle is a special case of that we've just had a look at. So as I said, they're essential to the study of astronomy, and their formulae are the circle, which is x squared plus y squared equals a squared, and that's an implicit function. We also have the ellipse, x squared over a squared plus y squared over b squared equals 1, which is also implicit, as I hope you can see. The parabola is y squared equals 4ax, which is explicit because x is defined in terms of y. And finally we have the hyperbola, x squared over a squared minus y squared over b squared equals 1, which is again implicit. And they're called the conic sections because we can get them from a cone. So the circle comes from cutting the cone across parallel to its base. The ellipse, then, if we tilt, we get an ellipse. If we tilt more, then the parabola is a sort of special case, and that happens when the plane that we are cutting down with, the purple plane there, is parallel to the slope coming down opposite to it. And then if we tilt further, we get a hyperbola. And these all happen within astronomy. We get ellipses for orbits and so on. I'm not going to go into the detail of that, but you can look it up if you like, or you maybe already know. So since they are used in astronomy for describing the motion of objects, then we need to know how to apply calculus to them, which we will look at in the next video. And that's just an example of an astronomical situation with an ellipse. Okay, we can also make some very difficult and strange functions using implicit functions. In economics, in certain situations, we might have that the price, in which we give the label P for price, obviously, and quantity is Q, and you can see which axis these are going to be on in a moment. And they're related by this equation, p squared minus pq plus q squared equals 400. Now this isn't the place to go into the detail of that, but that's the sort of equation you might turn up in economics. And if we graph this, we can see that it's not like an ordinary explicit function, because it sort of goes back on itself. So if we think of the value of x, or in fact p, but the value on the x-axis of 20, then does 20 map to 0 or does 20 map to 20? Well, it maps to both, and similarly for a number of other points. So it's not like an explicit function in that sense. And then you might use this graph, which again we're not going to do now, but the sort of question you might be interested in is, when the price is £4, estimate the percentage change in profit if we increase the price by 1%. And so these values will be then related into profit as well. You also come across some interesting functions in A-level questions. So these are sort of pure functions. They will pop up somewhere within mathematics, and possibly they may be used for modelling something. But what we're interested in here is looking at how weird they are. And if you want to have a go at just playing around with this, you could pop them into GeoGebra or another dynamic software. And this is what this looks like. So it's definitely nothing like an ordinary function. Again, we've got that situation where x values have more than one y value, and so it's weird, or difficult and strange, as the title of this page says. And here's another one, and this time we've got some powers in there of x, then we've got a trigonometrical function, and then we've got x squared times y cubed. So very weird and wonderful. And if you could sketch this from that, that would be amazing. But it is possible, but we can do it nice and easily by just popping it into the software. But you can see it's an odd looking thing, and that's the sort of things we get with implicit functions. We can also get some rather lovely looking things, and I put maths as art question mark. You may think this is arty or beautiful or not, but this is the graph of 4 sine xy equals 1. And so that's another sort of weird and wonderful function.